Hi, my name is Khairil Alizi bin Abdul Halim, CD 190222. In this video, my friends and I will presenting about our dynamic project, which is projectile motion. Projectile motion is a form of motion adapted by an object or particle that is moved upwards near the Earth's surface and move along a curved path under the action of gravity. The object subjected to an acceleration of gravity, and the object is also called projectile, and the path is called trajectory. The only force significant that acts on the object is gravity, which is downwards. Because of the taking other force into account, friction from aerodynamic drag or internal propulsion requires additional analysis. The motion along the perpendicular axes are independent and can be examined separately. This was considered in kinematic in two dimensions, where vertical and horizontal motions are to be seen independent. The projectile motion breaks into two motions, which is one along the horizontal axis and the other is vertical. To describe this motion, velocity and acceleration are included as well as displacement. The components along x and y axis are important too. All forces such as air resistance and friction included except gravity. The component of acceleration are negative 9.1 meter per second square. The objective for this project is different angle with different velocity influence the range.
Hello, sir. My task is to find the methodology of our research and, of course, our mini project. So I divided into three main topics of the methodology to make it more convenient to be understood. In our methodology, there will be methodological approach, data collection, and method of analysis. It's three, isn't it? Our methodological approach is intended to relate the projectile motion with one of the well-known Olympic sport, which is shot put. The mechanism of shot put itself is a very way of convenient and compatible with projectile motion application. Shot put works when the athlete itself push, or put a metal ball rather than throwing them with only one hand, right or left. The aim of this sport is to deliver the ball as far as possible from a circle with a diameter of 2.135 meter. There is a few things that needed to be kept in mind when we play the shot put. Shot needed to be released above of the height of the athlete's shoulder. Shot only counted when it released by one hand. Athlete needed to remain inside of the circle until the ball landed, and it is prohibited to touch the two board, or some of the people will call it as stopboard, during the put. It is stated that the weight of the metal ball is different between two sexes in the competitive international level, which is 7.62 kg for men and 4 kg for women. We can relate that one of the technique to release the ball is we need to push or put the metal ball, above of the height of our shoulder. This technique turns out to be applicable with the concept of our research, which is projectile motion. Logically, the angle of the release during the put or push has its own diversity. Even the same athlete perform in a few rounds. The position and the angle of release. Based on the data that we receive, it is proof that there are some quite significantly difference of the angle of the release and the velocity recorded on 6 rounds. We can conclude that the range is absolutely different based on the angle of release and the velocity, but this is still theoretically, isn't it? Projectile motion contains two components, which is horizontal and vertical. It can be calculated separately as it is independent to each other. To achieve the experimental value, these quantitative methods will be used. The first, the vertical distance on how far the ball will fly on the air. The height, the maximum height. And second is the component of velocity, horizontal and vertical. Next, the resultant velocity, and also the angle of the release. And last but not least, range of the ball that show how far it will go.
In the calculation part, we use the Microsoft Excel spreadsheet by insert a certain function to calculate the value of time t, velocity x component vx, velocity y component vy, total velocity v resultant, final angle data, and the range x component sx. The calculation will conclude 6 rounds and a 1 round of average. The final result will be presented in a table. The function that we use in our calculation equation of projectile motion for both component x component and y component. And the constant value in our calculation is the gravitational acceleration, which is 9.81 meter per second square, and y naught s naught y, which is the height of the athlete at 1.97 meter. After our final calculation and the value we got from the Microsoft Excel spreadsheet, we can conclude that the shortest range in X component is round 1 with the range of 9.97 meter, while the longest range in Y component is round 5 with the range of 30.23 meter. At the first round, the angle of release is 37.13 degree and the velocity of release is 8.97 meter per second. While at the round 5, the angle of release is 34.19 degree and the velocity of release is 10.7 meter per second. Overall, the average angle of release is 35.2 degree and velocity of release is 10.42 meter per second, which resulting the average range is 12.35 meter.
Okay, now I will tell you how we arrange the formula in the Excel spreadsheet. So first, we need to decide first which is the constant value and which is the value that we need to change. So for the constant value, we choose the initial distance and the gravitational acceleration. For the value that we need to change, which is angle and also the velocity. So you can get the velocity and the angle of the angle in the each round. Okay, first for the That's why I think this is the hardest part to arrange the formula in Excel, because we need to get to arrange the formula in the form of quadratic equation to get the t. So we get that after we arrange the formula back. Next, for the Vx, as we know, we use the Vx equal to Ux. So if we z, we just take the d4 part and multiply it by cos. We put radian there, so it gain us for the radian for angle. So we take the angle of h4 there that we put earlier. For the Vy part, we use equation u plus at. So take u as d4 multiply by sin h4 plus h2 and multiply by okay, for the part we calculate e is actually square root it by v squared, which is we take at c14, so we need to square c14 and then we plus by v1 squared, which is take at c18 and you square by 2. For the angle part, we need to take tan vy over vx. So vy as earlier we get at c18, then they multiplied by c14. Okay, for the last part, we need to find the distance at x. So we use the equation ut. So at d4, we put the formula d4. So d4 need to translate first into x. So we get d4 cos radians h4 for the angle and multiplied by c9 for the time. So that's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fathan bin Ahmad Fazuli. My metric number is AD190076. I will proceed to our project discussion. Basically, there are several findings for calculating the range of the object which is thrown from a specific point. In a projectile motion experiments, the horizontal range labeled as R and the time taken of flight labeled as T are essential, or in other words, they are really common parameters to be observed. There are three kinds of projectile motion that we already researched. For instance, horizontal projectile motion, ground to ground projectile motion, and one more is oblique projectile motion from a specific height. As we conducted, we only consider on two conditions, which are horizontal projectile motion thrown from a specific height and the oblique projectile motion which is thrown from a specific height also. As for horizontal projectile motion from a specific height, we apply it for angle theta equal to 0 only. Which means that the athlete or the model of our experiments throw a short part horizontally forward without considering any bend in angle of his arm. The formula for horizontal projectile motion to calculate R is R equal to K times U to the power of M times H to the power of N, where K, M and N are constants to be determined in the experiment. The value of G, as we know, is included in K. First, a graph is plotted against the log of range r versus the log of velocity u. After that, the slope will give the value of m, like the following picture. Second, plotting graph. The graph is plotted against log of range versus log of height, labeled as h, and the slopes obtained gives the value of n as follow. Hence, the new formula, when we substituted the value of m and n into the previous equation, is r equal to u power of 1 times h to the power of 0.5 times k. U to the power of 1 because we round off the uh, receive result from the slope. After that, the value of k is constant as k equal to square root 2 over g, where g is due to gravity, and from the substitution square root 2 over 9.81, the value of k is 0.46. By substituting the value of k 0.46 into the new formula, we got a general solution for the new derivation of formula, which is r equal to 0.46 times u times square root of h. That is the general formula to calculate range for horizontal projectile motion which is thrown from a specific height. Okay, we continue to the oblique projectile motion. As for oblique projectile motion, the projectile motion can be analyzed by considering two directions of motion, which are vertical and horizontal motion independently. The oblique present angle theta from 0 degree until 90 degree only. This is the most suitable formula because the method of throwing short putt is between the range 32 until 37, which was demonstrated by our athlete model. The motion along vertical direction can be described from the kinematic formula, which is delta x equal to v naught t plus half a t square, which a represent gravitational acceleration and v naught is represented by u sin theta, and value of x represent the h. The sign of h is negative because the direction of short putt is directly downward. Meanwhile, the motion along the horizontal direction can be described using the equation r equal to u cos theta times t, because there is no acceleration regarding x-axis. It is only considered by y direction. Finally, the derivation of both formula gives a new general solution for oblique projectile motion as below. Where the value of v is the projection velocity, theta is the projection angle, h is the height difference between the launch and the landing, or also known as the height of the athlete. H is our constant, which is 197 cm, and the value of g is the acceleration due to gravity. But we need to bear in mind one revolution equal to 360 degree, or equivalent to 2 pi radian. So we need to convert the angle to the radian first before substituting the value of theta. In short, from the discussion, we only consider theta between 32 degree to 37 degree. So we only apply the oblique projectile motion from a specific height because the athlete did not throw the angle at 0 degree, which is horizontally forward. So therefore, the horizontal projectile motion formula of derivation of range is not valid for our experiment. Plus, the horizontal projectile motion derivation formula of range is only for our additional knowledge, and it is not included as our main calculations. Thank you.